Good morning. Today is Friday, the 3rd of August, 2018. This is the nybbles.io daily programming stream. My name is Jeff, and template code is so fun. I write code every day, and I stream it here on Twitch. I'm working on a project called Basecode, which is a new programming language. This is the Bootstrap compiler. It's written in C++. And right now I'm trying to fix bugs. Oh, crap. Okay, that's wrong. Yeah, that's okay. That's what I've got printed. Oh, I guess I don't. There. What? Okay, so now is it bitching about this? Probably. Yep. There you go. Ooh. So what I'm doing here is type inference is not working for signed values. And that's because first the narrowing function wasn't really considering it. All right, so yeah, we're still not landing in here. Should be though. Those are unsigned. Interesting. We're never getting the... Because it's there. It's in memory. And that looks correct. Oh, I think I know why. I had it in here, that's why. Oops. That would explain it. Okay, so it's still negative. So it might be inferring it correctly. I don't know. Put the breakpoint back in. Yeah, okay. So it's seeing the sign bit now and start end. So this, we're looking at S8. It doesn't fit in an S8. These are probably not 2's complement. I just realized that. Because I think it's skipping. It should fit in an S16. Yeah, and so see, it's falling down. Yeah, it's not finding them. Okay, and I think the reason for that is, what is this? Yeah, it's an actual negative value. Hey, Slayer Darth. Oops, do that one. So the question is, how do I want to store this? Yeah, I'm wondering if how I want to do this. Because if I converted these to 2's complement, I'd have to create my own comparison function, which I could do, but yeah, I'm kind of, at least for the moment, sort of cheaping out here a little bit. I'm just saying, okay, well, if we know we're going to be comparing to the signed range, let's just let the C++ compiler turn it into a signed value for us, and then we should be good to go then. Well, I don't know. We'll see. Yeah, that's what I was going to say. That's not going to work. My original. I really don't want to do it that way, but not a huge price to pay, I guess. So we can always just cast and have the signed version, and not a big deal. Yeah, so we should end up here for the signed situation. No, it worked. That proves that my two's complement thing's working, right? Because the C++ compiler was able to convert it into a signed value properly. What are we on? We're on S32. Hey, Dr. Robot. The signed value is negative 22768. Crap. It's going okay. I'm confused. All right. Signed value is negative 32768, which is correct. The first one we're checking against is an S8. So is signed value greater than or equal to the min? No, it's not. But it is less than the max. So we skip that one. Now we're on S16. So props min is 32768, so it's greater than or equal to that. And props max is 32767. I mean, that's the one it should be picking. Yeah. So, see, the compiler did not catch that, interestingly enough. It did not flag that as warning. Very interesting. Okay, so now we are inferring, but see, yeah, so that's another issue. But we are inferring the right type now. So we are inferring the correct type. And S is being used as so I7, yeah, so it's loading a 16-bit value. All right, so that's correct. Okay. And float literal. At least for now, I'm going to say, or do I want to? So we're going to have two of these. One that takes a double and one that takes the integer. Yeah, I'm going to come back to this one. For now, I'm just going to narrow to an F32. But at least now this is all in type. It's not in a couple different spots. And the endpoints that are needing to narrow, they can just call narrow, and we're not hard coding the number values there any longer. So that's good. So make sure I didn't break anything. Yeah. All right, let's look at this real quick. So in bytes, which is where I kind of put all my binary, byte manipulation shit, I've got two template functions now. One is signed bit set, and it's templatized, so I'm not putting any constraints on here, but it should just be numeric types, obviously. And the compiler's gonna complain, right? If I pass something in here, it doesn't make sense. But the sign bit is always the most significant bit on the left. So we take one, and which is just, that's the least significant bit that's turned on. And then we cast it to the size of t. So if we pass in a 64-bit integer unsigned, it's going to be 64 bits wide. We take the size of that type it comes in, we multiply by chart bit, which is how many bits there are in a character. So that's going to give us 64. We have to subtract 1 because it's 0-based. And then we do a logical AND, or binary AND, against that value to see if that bit's set. And if it's not 0, then it's set, and that's true. Then I added just a helper function that will take a given numeric value. So if it's 8-bit, if it's 16-bit, if it's 32-bit, 64-bit, and it will do a binary inversion on it, right? So it's going to flip all the bits, and you add 1. That's how you get the 2's complement. So if you have, 126, you invert that, and you add 1. That causes the bits to roll over, and that gives you your 2's complement. Float literal, I added an is signed accessor on this, and then in the CPP file, if the value is less than 0, it's signed. For floats, we probably don't need that too much, but I thought I'm trying to be consistent. So integer literals have it, figure floats, which can be negative, can be signed. They should have it too. I updated on infer type in float literal to call narrative value, which we have now an overload for floating points. It's currently returning F32 hard coded. We'll get back to that. But structurally now it's much closer to what it should be. Integer literal has an is signed, and that uses the is signed bit set because, so the compiler is, so everything is an unsigned 64-bit integer in the infrastructure, really. And floats, floats are kind of weird, but floats are treated as a 64-bit integer too, because that's what they are, but at a binary level. But anyway, so in order to determine, I can't just say, is this integer less than 0? It's not signed. The C++ compiler doesn't see it as signed. In some situations where I did this in the numeric type, I could kind of cheat a little bit and cast things within the compiler tooling, I guess, or some of the support infrastructure. But a lot of stuff that's going to surface out to actual bytecode or native code has to be consistent. So we have to check the sign bit here to say whether or not it's a signed value. And obviously in a 64-bit integer, the signed value is going to be a very large number because there's going to be a lot of high bits set. And that's it for that one. And then in numeric type, like I say, I added an overload to narrative value. For floating point, I'm probably gonna have to write some custom range stuff there because there really aren't good limits set for that. So I'm gonna have to come back to that one. For the integer narrow, what I did was, I know that within our list of types, numeric types, I have a range. I have a range of unsigned, and I have a range of signed. And then I take the value that comes in and I convert it into a signed value for the C++ compiler. So this is a two's complement value, which the C++ compiler is like, oh, okay, yeah, I can do that. And so that it actually turns it into a properly signed value. I loop over the range that I chose, grab a property. If it's signed, then we do our comparison there. The only thing is I have to make sure I cast the right-hand side to a signed value as well, because otherwise the comparison fails. If it's not a signed value in the property we're getting from the map, then we just compare it to we just do the normal compare. And this then finds the correct signed integer type that fits that. In program, I added that helper function, to's complement, that just takes, it's a template function that takes the to's complement of whatever value you pass into it. And it's scaled, right? It's based on size, so so that's good. And then in our test program, I got rid of the type so that the inference can actually happen. The inference is working now, so we can get rid of that comment. So that bug is fixed. There are so many more. Okay, the next bug we gotta look at is, okay, here, what's happening, it's not really a memory alignment issue, I don't think. I thought it was originally, but there's something else going on. So if I do this, if I create S and I say it's an S16, okay, and then I assign S to this value here, and we'll just move this print up. This, I think, works. And there's one difference between the two of these, which then kind of points at the interpreter. Well, some of the interpreter. Okay, well, we're getting a positive value. And that could be because of how I'm doing the printf, maybe. No. I really don't like printf. The format library is so much nicer. The problem is the format library is one of these examples of it's type safe in C++. It isn't dynamic. It's all compile time, which is nice, but in this situation here where I'm calling something and dynamically passing a bunch of stuff in memory, like, it doesn't really support that. So definitely one of the very first things we will have to do is write our own formatter, our own string formatter and stuff. So I'm not sure why. Oops. Okay, yeah. So, all right, let's do this. Let's say it's 32-bit, so that I think I think printf is, I'm either using the wrong format specifier or I'm not sure. I know if I make it a 32-bit integer, then it behaves properly. Well, maybe not. Yeah. Weird. All right, so now if I make it S16, I mean that's correct. The value's right. It's not showing it as signed though. I'm not sure why that is. Very strange. I guess let me just do a sanity check here. That yeah, because that's the upper limit 32768. Because 32767 see all these other bits are set. If we do 2's complement, well, yeah. Crap. I wish there was a way in this calculator you could say you could change the size. Yeah. So the high positive range for a 16-bit is 7 FFF. The high negative is, and you'll see here that the sign bit's not set, right? So it's the right value in memory, seemingly. We are passing, oops. What is C, printf 16-bit signed. Is it just H? Yeah, it's just HD. I think that was the mistake I was making. HH is for byte. Okay, so, all right. So actually that's working. So can I break it? Well, oh, A's busted now. See, A is 0. Yeah. Okay. So it just shifted. That's all. So if I move this down here, B, C, D, A probably be fine. S is probably going to be messed up now. Yeah, A's messed up and S is messed up. So B is 6, C is 7, D is just a slot in memory somewhere. A is 2, which is correct, but when we're trying to store back to it, something's getting stomped. So what is A? A is I12. And we're storing a byte. I mean, seemingly that would be correct, but and then, yeah, S is like, even though I think the value in memory is fine, yeah, it's not, we can't load it for some reason. We're getting a 0. And so I should be able to take that out. So it's not really, it's not just signed integers. There's something that's off. Not sure what. It's just a memory alignment issue. So here's where we're loading S, right? Here's the address. Here's where we're loading the value. We push the value, we push the string, we push the number of arguments, and we call the foreign function. That is at address 340. So here's what we're gonna do. This is gonna be like the ultimate in poor man's debugging. If registers program counter is equal to 340, what this will do is let us run it. It'll get to that point in the interpreted byte code. Then our C++ breakpoint will hit. For whatever, at some point I'm going to try using CLion's conditional breakpoints again. See, that right there makes me think, because it's showing, oh, but it's 340 hex. Damn it. Darn it. To see if they work. In the past, they just haven't worked consistently. I'll tell you what, the Watcom C++ compiler back in the DOS days was a miracle of debugging magic. It had some really cool shit in it. You could, conditional breakpoints always worked. You could trigger events after conditional breakpoints. So like if something happened, then you could trigger breakpoints at other parts in the code. It was pretty slick. Okay, so this should be a move instruction, which it is. So the source value is 358. I forgot to cut and paste that. And then we're setting the target offset 0. So let's step into this. All right. So then the register is 13, which that, yeah, it's the, is that right? I don't know. I can't remember. Right, and this is just a 64-bit value, so we just assign it directly. This should be the load. Right, so the first was loading the address into I13. So address is 358 because that's what we just put in I13. All right, so this I think is where we're getting in trouble. So the address is 358. Now that's an offset relative to the beginning of the heap. So we step into this, we have a heap pointer. So that is this value here. We're going to add that 358, and then we're going to dereference the pointer we get back, and value is that signed value. So if I where's value? If I copy that and I paste it. Okay, that, yeah, it doesn't seem right. Not right. Okay. So it's what I thought. I'm doing something wrong here with the pointer aliasing. So then we're putting bullshit in that register. And so then when we come back, this is going to be a push, right? And yeah, and now we're getting 0 because yeah. Because it was I16, yeah. I13 had the address, which is right, but I16 is just this garbage. All right, so I think this here is the problem. So heap is a uint8 pointer, so it's a byte pointer, right? So I think what I'm going to have to do, which isn't a big deal, I think what's happening is when so addressing memory at the byte level, no problem, right? But as soon as you start casting up to larger sizes, then you potentially get platform dependent alignment and other things that crop up. And like I'd have to look at the disassembled code at a call site to see what it's doing here, but my guess is it's just not doing the right thing. Hey, cache override. I think it's doing pretty good. I make slow but steady progress. Like that. Okay, there could be multiple problems here. Oh boy. All right, result. Oh, What? I'm confused. Yeah. Why would I set result to the register? I'm not even really sure what I was thinking with that. So we call set target operand. Oh, I think I remember maybe what's going on here. It's been a while since I looked at this code. Yeah, I think originally I had this I had other things going on. And I think the source value was, or the source was being used for something else, but then I think, as you know, it's an example of a refactoring where I didn't like completely finish it the way I should have. I think set zoned value, it's set zoned value at some point was actually like updating registers itself. Oops. But yeah, like randomly setting the value and then handing and warring stuff into it. That would have been bad. That would explain why some weird shit was happening. Yes, yes it would. I love it. So you know what I'm gonna do? I'm just gonna revert that right there. And so result starts off life as whatever value comes in. And then we do our magic to it. So, and then I'm not setting result to the register number, the register index, which is like, has no meaning whatsoever. I would have been amazed. I mean, really, so far, and I did put some time into it up front, right, to test it, the interpreter. But I mean, I've been amazed at how really few issues have cropped up in the interpreter. So I was due for something silly like this one. Not to say that there aren't other bugs in there. I'm sure there are, but okay. All right, so result matches value. We yeah, it's not right. What was I thinking here? So what does set zone value do? What it's doing is maybe I had that right. I don't know. What was I thinking here? Okay, it's coming back to me. For a guy who has horrible memory, I worked on this in May, the interpreter. Okay. So here's what I think is going on. So what I'm doing is, I'll take one of these, doesn't matter. So we're doing this right here, right? So what I'm doing is I'm looking up whatever the current value of the register is, and I'm passing that in. That's what the current value is. Value is going to be the new value. I'm passing the instruction size in. I'm not sure. Okay, that's because that's what's telling us what the opcode sizing, what the zoning size is, right? So how does this work? Okay, so again, all registers in the interpreter are 64-bit. They're always 64-bit. But if you say, I just want to put a byte in here, then what we want to do, so we're assigning result to whatever the current value is. So let's say you have a 64-bit register and you have a 32-bit value in it, but for whatever reason, at the assembly level, it makes sense to just tweak the byte or the 16-bit, 16 lowermost bits. The other bits stay the same, right? And again, because maybe you're doing a load and you're only looking at the byte, or you're only looking at the lower 16 bits, the other top bits can be ignored. That's a fairly common behavior in assembly type low-level programming. So what's happening here is we're taking the original value, and the intention I had is I'm supposed to be clearing out the part that I want to. These are the bits that are important for a byte. To clear that, I'm taking the inversion of that, the binary not. So then that should make all these bits 1 and these 0. And so then, if I take the result and I apply the mask to it, it should be dropping out. It should be keeping all the bits but the lower 8. And then I'm ordering in the value that we're passing in, and I'm only ordering in the lower 8 bits in this case. So I'm taking the value comes in, whatever's in it, and the lower 8 bits, I'm putting those into this after I've dropped out the lower 8 bits. And this would be the same thing. So let's do this. Let's print word result equal I think B after clear, and then let's do this. Let's take that, put it in the temp, I am working on a project called Basecode, which is a new programming language, and right now I'm working on the compiler for it. Okay, so what we're going to do is we're going to dump out the binary of result before we clear it. We're going to dump it out after we clear it. We're going to dump out whatever value is and the mask that we're applying to it for a word. And then we'll dump out the final one there. All right. It'll be interesting to see if I got the format code right. I think I did. So I guess I could logically say well, I don't know if that's true or not though. Okay. Okay, the word result before the clear was 100. Yeah, that's not right. Okay. So that's correct. That's 4. So for whatever reason, that address not saying, hey, just watch some of your viewer request broadcasts and those have been absolutely great. Awesome. Glad you enjoyed them. Let's see what those masks look like. Just as a sanity check. Okay, that's exactly right. Okay, so these are the bits we want to preserve. These are the bits we're going to replace. So the very first thing we do is we and result against that mask, this mask, right? Which now all those upper bits are 0, so we drop out those lower bits. Great, okay? So that's actually correct. This is correct, that's correct. This is not correct. Unless value 0. If value 0, then of course that's a different problem. But value is it's not 0. Crap, I didn't mean to hit F9. Now there's the problem right there, right? Value So if I take that value and I paste it in here, and then we do an AND, six, 5, 5, 3, 5, right? Yeah. 0. Huh? No, that's correct. It's here. I'll try to explain it again. It's correct. It's the right decimal representation of it. I'm thinking about this in terms of binary though. So I have two masks. One is the inverse of the other. One is a clear mask, meaning that these are the bits I want to drop off, and then these are the bits I want to keep in this case. So so this bit mask, this is 65536 or 35. This is this lower 16 bits of a 64-bit integer. These are the remaining upper 48 bits. But when I and this mask with this value, it's getting whacked. I don't understand why. No. What the fuck? Oh, because wait, I know the mistake I'm making here. At least in terms of how I'm understanding the problem. I think I might still have it in my clipboard. No, I gotta get it again. This is why, like, it's so much easier sometimes to look at these things as binary. I think the mistake I'm making is I'm looking at this number as decimal and saying, oh, well, there's something there. But if we copy that and I paste that in here, there isn't anything here, right? These are all 0 bytes, all 0 bits. Only this bit is set. That's 63, 62, 61, 60, 59, 58, 57, 57. What the fuck? I don't know, right? So that's probably a random value. So actually this code's probably fine. It's just that there is nothing there in those lower bits. See, that's where you can get kind of, you look at it as an integer or, as a decimal, and it's not clear, right, that those would all be 0 bits in that situation. But that's actually what's happening. Okay, so then that rolls me back to where I was before. Somehow we're not reading from memory correctly. darn it. So I think what I'm going to have to do is I think I'm going to refactor these. So instead of having this byte pointer, word pointer, quad word pointer, doing it this way, I think I'm just going to on terp have a peek and a poke. And you'll pass in a size and you'll pass in an address. And then we'll have a switch in each of them, and we'll address everything as a byte pointer, and then we'll have to do our own byte adjustment for the larger types. Because I think, I'm guessing, that's why I'm trying to print out this address. I think what's happening is we're aligned within the relative space of the terp's heap, but we're not aligned necessarily as far as the machine is concerned. So these are the actual addresses in real memory that we're trying to access. So this was the load, right, that ends up calling set zone value. So that load is it it's not on an 8-byte boundary though, right? An 8-byte boundary would be 0808080808. Or I'm sorry, it'd be 08 no, it would be 080 because 8 plus 8 in hex is 10. Yeah. So the only two valid values here are 08. And you'll see a bunch of them are, right? A lot of them are, where we're accessing things at 8-byte boundaries, they are in fact 8-byte aligned, but this little fucker isn't. This guy's off, right? And this is gonna happen sometimes just because of the order of the way things are. And the thing is, right, here's where it gets interesting, okay? So, I'm going to close that. If we look at this, just relative, so there's a pointer somewhere in memory in the real machine that has a value, right? And that value is probably on this machine, because it's a 64-bit machine, it's 8-byte aligned. It may even be 16-byte aligned, I don't know. But I'm going to assume it's at least 8-byte aligned. And if you look at the real addresses, that does seem to be the case, right? This ends in 0. And then the very next address is 8, and then 0, 0, So I'm going to assume it's 8-byte aligned. Now, from our perspective inside the interpreter, everything starts at 0. So it's 0 from that pointer to the top of our heap, okay? So within our relative space, we can say, oh, stuff's aligned, right? So this is a 0, this is 4-byte aligned to that. So in other words, this is like an 11-byte, 12-byte? Yeah, 12-byte encoded instructions, so that gets us to AC. That is on a 4-byte boundary. And so that's fine, right? And then we come to the next string. We ended at E0. So then we align to E4. And then this ends at F1, which would definitely not be 4 byte aligned. So then we align to F4. So again, but this is relative to the start of our heap, not the overall address. So at some point, and I think, I just ran into this, we're going to be aligning things within the heap, and our relative alignment is going to be off. From especially, now it's not off if the smaller you get, the less that this happens, right? So 2 byte alignments, 4 byte alignments, it's not going to be that prevalent of a problem, but the 8 byte alignment is. Now, we could fix this a number of ways, right? One of them would be just to force very large alignments on a lot of this stuff and burn some interpreter heap space, and with the intention being, we know we started 8 byte aligned, so like the minimum alignment for everything is 8 bytes, whether it uses 8 bytes or not. So like these single bytes, these would all get aligned to 8 bytes. Everything above it would get aligned to 8 bytes. We could certainly do that. And realistically, when we get to the native code generation point, that's probably fairly accurate. But again, some of that depends on the target architecture. So on x86, if I am doing some word and 32-bit and byte type stuff, I don't necessarily, the CPU will cope with it not being 8 byte aligned. But if I'm doing 8 byte, if I'm doing 64-bit accesses, then it has to be aligned. And so I think what's happening, right, is I'm trying to cast this to an 8 byte, a 64-bit pointer, and this is not an aligned address. So it's doing what it's told to do. It's saying, okay, well, whatever is there, but we're off, right? So at that point, we're off, and bad things happen. So like I said, the way we would probably, an easy way to fix this would be we index everything as a byte pointer because there's no alignment issue there, right? The CPU is going to deal with that for us. And we know when you're addressing everything at a byte level, you can point at any byte in that heap, and you're fine. And then we would just have to, kind of like what I did in Ryu, we would have to do our own, okay, you're doing a byte, all right, write the byte, simple. Oh, you're doing a word, okay, this is little endian, take this part, put it in there, take this part, put it there. We would just have to write the bytes out ourselves, is all. Instead of going through the C++ compiler, trying to cast it. So let's do that. Size, address, size, address, value. Now there's another potential problem here. Big switch. Okay. It's right in front of me. Oops. Oh, I already had a peek. Oh, that's looking. Oh, that's a different peak. Okay. That's peak for the stack. Okay, so then for stuff internally that was using that, this would be peak, op sizes, keyword, heap vector address. So what? Hey, Slayer Darth. Oh, I'm passing it as a size T. That's why. Okay. Now see, the C++ compiler is going to guarantee that this is addressable on the right boundary. So Yeah, for now, I'm gonna only do little endian. And I think if I don't have in here, I have some code in Ryu that kind of abstracts this process. So I mean, I'll probably just gank that code and have a general helper, right, that does this. But okay. So that's, yeah. So the reason this will work is, again, because these are now not, they're addressable by the interpreter, but they're not directly addressable by the outside world as the types that we say they are. The bytes are there, they're just not aligned to the outside world in such a way that they could be accessed, especially at this size. Now, with that said, that's okay. The only thing that's potentially a problem excuse me, is here. So the one thing that could potentially be an issue, but we can solve this, right? We can force this to always be we can set up things in the interpreter heap such that anything that is a pointer that would go to the outside world is on an 8 or 16 byte boundary, essentially. Because, like, as an example, the strings, those are pointers that leak, if you will, when we call a foreign function in another shared library. We're literally passing a pointer to that location in the interpreter heap. So when we call printf, right, or in this case we're calling vprintf, but same idea, we have to take the heap pointer, add our relative pointer inside the heap to it, and pass that. That's a real pointer. Now, there's a couple things here. Right now, I'm temporarily pointing at string literals. Realistically, we probably aren't going to do that. So we can make sure that when we do create like the actual string types and other things where we would pass pointers to them, like structures and things, that we're aligning those always on an 8 byte boundary. It's a true 8 byte boundary relative to the heap pointer. So, which means in the interpreter heap, we might occasionally have to burn extra space to get, or we might in fact have to use less because it just so happens that to get to that correct global 8 byte boundary, it's a shorter jump. So that's one area we're going to have to come back to. Are those two still? And I think there's other code that was using those accessors, so I could probably try to fix those two. Oh, yeah. You know what? Let's just call. Right. Okay. Now we just got to do peak. Oops. Result. I just realized I did this wrong. No, because I already put them in order, right? In the heap, I've already put them in little endian order. So when I populate the actual underlying type, I can just read them in sequence. Yeah. I know there's going to be a couple other places we'll have to touch up. See, the nice thing about, well, I say the nice thing. Right, so this is going to be terp, right, op sizes, byte, entry address, data def. Here's a nice side effect. There you go. Nice. What was I going to say? Yeah, for numeric values, for a lot of things, right? We're passing the values of things. We're not passing the address. I mean, we are passing pointers around, and we will have to accommodate that, but I do that in the right order. I can never remember. Ram. So writing a word, we get the byte address of the value, and in memory, the first entry is, oh, I think I did this backwards. Yep, I think I did this backwards. Oops. Oh. Easy enough to fix. Yeah, I guess that makes sense, right? Because I'm just assuming it's little endian, so I'm just copying the bytes in there. Yeah, and then to read it, it's the same thing. Just so we've already cleared. We've allocated a 64-bit integer on the stack. We've cleared it. It's set to 0. So all the bits are 0. So then we're going to poke in values. So this is where I'm off. Because this is going to be an array of 8 bytes. So little endian, actually no, this is right. Yeah. Because we just, yeah. Because the end is the most significant. All right, I think that's good. That's one of the advantages to little endian, is that you can just poke values into a larger type from the beginning. You don't have to do, as much swapping. But we'll see if I got it right. If it blows up, Well, didn't blow up. But we're still not getting shit. Seriously? Oh. Well, we're never calling. Never calling read. Right. I think I botched it. That's why. There you go. Boom. Fixed. There's A, there's D, there's S, and it's showing up as signed. So, and look, so the original value here was 4. We cleared it out. Then we put the negative 32768 into the zone, right? And that's exactly what we wanted. So, okay. I'm going to say that I fixed that issue. So let's do this. Let's go back to the interpreter. Just leave that in there. I'm sure we'll have other cases where I need to debug that. All right, that looks good. Very, very good. All right. Very nice. Okay, so in our test file, I fixed the type inference, I fixed the alignment problem, which is it's more or less what I thought it was. And so that refactoring is going to go a long way for future things like that. Plus, I think this is cleaner. Just read write, you pass in the size, the address, the value, or you get the value back, and instead of doing this other shit, just a cleaner API. So now pop and peek, which are working on the stack, they use the read, and those are always 64-bit values, so that's fine. In step, so we call step repeatedly for the interpreter to run. I just put a block in here that I can uncomment if I want to have a breakpoint on a particular address in an interpreted program. I think there were actually two problems here. One is that I wasn't honoring the size on the instruction, and the other, I think, was the alignment. So it's both of those together that were important. So load the store were really the big ones, right? They both needed to be reworked to use this new read and write. The SWI instruction, it reads an offset from the heap, which is always a 64-bit value. A lot of these are always 64-bit. But again, some of those opcodes do work on different scaled sizes on that register. Pushing onto the stack. So we just use write now and we pass the size. Again, the stack is always 8-byte aligned. The SWI, so when you want to register an SWI, so SWI is software interrupt, so you can tell the interpreter, hey, at this SWI index in the vector table, go to this address, right? And so that's writing that address into the heap. Read. So we always address our heap pointer as a byte pointer, and we get the address of our temp variable here, and then based on the size we're asking for, we just read the bytes out and stuff them into that result. And yeah, this is just setting, so again, heap vectors. The heap, early on in the heap, there's a little table where we can basically point at, hey, does the stack start? Where does the stack end? Where does free program memory start? There's all these pointers, basically. They get stored in this table. So this is the mutator for that. This is the this is the accessor. This is the mutator for that table. And they just vector then through read and write. Those are always 64-bit values. And then write. Again, we address the heap on a byte level. We take the address of the value that we have passed in, which is always a 64-bit value on the stack, on the C end of things. And then if it's a byte, we stuff the very first byte in. If it's a word, the first 2 bytes, and so on and so forth. Yeah, I think that just reads a whole lot cleaner. And then in assembler, for data definition, we were telling the interpreter, hey, stuff data here. And this nicely shrunk up because now write just takes the size. The data definition thing has the size on it. We just pass the size, the address, and the value, and done deal. So all that's much cleaner. Okay, there's one last thing I'd want to take a look at. So we look at the output here. We're going to see that we move the address of this variable here, this S variable, into I13. You'll see that when we load the value, we load it as a 16-bit value. That's correct. You'll notice, but the push then does a 64-bit push, which this is kind of bizarre. Sorta. Really what we're doing is we're giving intention here more than anything. This should just be a word push. We're still pushing a 64-bit value on the stack because that's the size of a value on the stack. But we're telling the interpreter, and then later we're telling the code generator for the native stuff that, hey, this is just a 16-bit value here. And maybe that helps and maybe it doesn't, but I would like to have that flow through so it's accurate. Now, this would be a quad word push because this is an address, it's a pointer, and pointers are always the whole thing. So how do we do that? Well, if we go to variable t, Yeah, so in argument list, I think what's missing yeah, this is just hard-coded. So let's do this. Let's say op sizes, push size is op sizes keyword. And if we get a value register, push size is equal to that. And this will just be push size. So we default to a 64-bit zone. And if we actually have a variable and it happens to be a value, we know what size it is. We update the size. And the survey says ka-ching. So that's exactly what should be, right? And again, does this actually functionally change anything right now? No, but it's a hint, right? And so why do we need the hint? Well, again, when we convert this byte code into native code, we're going to have metadata and other things in the stream to help the process, but it also will help when we're at this instruction and we say, oh, okay, well, I11 happens to be a 4-byte thing. It just, gives us a little bit more contextual information without necessarily having to have lots of other stuff with it, right? It's just it's one of those things, again, where it just makes things clearer. We need to do the same thing with like the arithmetic and relational operators. It's not passing that through. These are all specifying the full size. Very good. I am so happy about that. All right, so we fixed the argument list. So the default size for the push instruction is a quad word, but if we actually have a variable and it's a value type, we get the size, the op size, based on the size of that type in bytes, and that's the size we use. And that is wonderful. Hey, Everex. Okay, pretty good morning. Got 3 bugs fixed. And so what's next? So what's next is I'm trying to think here. I'm gonna, Yeah, there was there was a bug. There is a bug. I think the next thing will be this. If I try to assign b to that expression, something's not right. So that's probably the next bug I'll look at. And I think it's just what's happening is, yeah, we're calling, when we're creating the identifier in that case, I think I'm forgetting to call something. I'm not sure what exactly. Oh, I know what it is. I'm not creating a variable for it, I think. So add identifier to scope isn't calling context assembler or context allocate variable. That's the bug there. So I got to fix that next. I think that'll be simple. And then I think what I'll do is I'm going to restructure this a little bit. I'm going to create some blocks that test all the types. Bytes, words, dwords, qua words, signed, unsigned, floats. I know the floats and are going to be there's going to be bugs there, but just essentially creating all of them, making sure that the ranges and everything, all that works. I'll go through, like if I said that this was an S16, and I tried to make this negative 6536, that should be an error. That's going to be bad. And right now I'm assuming it'll let that pass. Yeah, well, and then I have the other issue. Here. And I made some incremental progress on multiple assignment destructuring. I'm still trying to think of how exactly I want to do that in the compiler. But yeah, it's just letting that go, which is bad. But yeah, see, 0, not good. So need to verify value ranges against declared types. I mean, obviously with inference, that's going to be taken care of by the compiler. It'll do the right thing. But if you specify the type and you put the wrong value there, then that's going to be a problem. And then, of course, because printf is stupid, yeah. So I think those are the next two things, right? Getting that fix into add identifier to scope, verify, I'm going to verify every numerical type, the ranges are all right, mins, max, the compiler bitches if you're outside. I also need to test like the parser and make sure that, I can specify all of the different values in all the different bases that I want to support. So decimal, hex, binary, octal, they all work. So I'm going to restructure this so that I can test all that and make sure that that's looking good. And then once I ferret out any remaining bugs there, then the next thing would be to test all the binary and unary operators against all those types. And I think also at that same time, I need to make up my damn mind about how I'm going to do casting, like what rules I want. I have rough ideas of what I want to do there. So then I think I need to start adding the assertions around whether or not something needs to be casted, and then we need to make sure that the cast operator is doing what it's supposed to be doing, which right now, not really. It's not verifying things properly, and so there's got to be some love there. And then when I got that done, but I think the next thing I want to do is work on, we're going to do anonymous scopes. So as a prelude to revisiting procedures and other things, I want to get anonymous scopes working. There's a parser bug, right, that needs to be fixed. I think this will be easy at this point, but it just needs to be fixed. And then what will this do, right? Well, this should create a stack frame and free stack frame, and then variables here are allocated on the stack by default. Okay. And then obviously we should be able to test nesting here, right? And it should work. So this will be next, because then if we can get that working right, then that is like 99% of what we're doing in procedures. And then we'll have a good foundation for revisiting procedures and actually then starting to get like our own procedures callable, and we can call foreign things. And let's get, I want to get it to where I can call my own things. Yeah. So the rules are going to be anything that's at the module scope is global, right? It's global in the sense that for the compiled code, at the bytecode and at the native level, these variables would be defined in the memory segment, right? Either read-only or BSS or data, but they're global. From a language perspective, they're scoped to the module, so you still have to go through either the module or importing to get to that symbol, but when it all gets turned into one big program from top to bottom, these will be always segment bound, right, in the final executable. Everything else that comes after that, so any other scope created from the module down, so if I assign this to a namespace, or it's anonymous, or it's a procedure, those are all on the stack then by default, unless of course then eventually we override the allocation and blah 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 blah. But that's going to be the general rule. So what that means then is variables that we create in this scope are A, only available in this scope and down, but B, by default, they're on the stack. So when we hit this point in the code, we're going to generate code that cleans that up. And when we hit the end of this block, we're going to generate code that cleans it up. And I think also as a part of this, we implement defer, because it's just a good time to do it, to make it work. So anyway, that is, I think, the order roughly of how I'm going to do it. And yeah, so let me look at this list here real quick. It's funny because like I'm doing a lot, but haven't like really hit anything. So, all right, but we're making progress. So let me just make sure that doesn't break anything. Okay, yeah, that's a known problem, so I'm cool with that. All right, let me check that in. All right, that's gonna do it for the day on the stream anyway. So let's see, is there anybody that, probably not, no. So Crosbo asks, will Basecode have public, private, protected things? And the answer is probably not. Again, like those concepts, those are concepts that you could easily build yourself by making language extensions eventually and metaprogramming. So if you wanted to have the concept of this extra level of access control to parts of scopes, you could build that if you wanted to. It's the same thing as like inheritance or polymorphism that's based on inheritance or anything. Basecode Alpha is, I really kind of think of it like an assembly language almost. Now, obviously it doesn't, Basecode Alpha is higher level than, you know, the bytecode assembly or native assembly, but I think of Basecode Alpha as a relatively low level tool set. And that's by design, that's intentional. Because again, if I hoist Basecode Alpha up too high, right, then by definition, I have to start making more constraints, right? And I don't want to, I want to leave that part of the tool set open so that you have all the power in the world, and with great power comes great responsibility. Then you can build all these things on top of it if you want. So if you want to take Basecode Alpha and then, you know, create a whole, you know, DSL language system on top of it that tightens it down to insane degrees, then you can do that. That's one of the reasons why, like, there's lots of high-level concepts, like in languages like Scala or, you know, OCaml or F# or whatever. But those things don't, in my mind, those things don't belong in alpha, right? Those are things you build on top of alpha using the metaprogramming system, and eventually the language generation facilities and stuff that I build in beta. And then the sky's the limit, right? At that point, you have this, you know, low-level language that has some niceties compared to other low-level languages, but is not crazy. You know, you're still basically building to the machine at that point, but you have these additional metaprogramming capabilities that allow you to then build all these more high-level concepts on top of that. So if you wanted to build an ultra-complex type system on top of Basecode Alpha, you could do that. So that's the general idea. Okay, who can we host today? Anybody have any suggestions? let's raid super circuits. All right, everybody, here we go. We are going to raid Basecode. Super circuits. So, everybody have a good day. I'm not streaming on Saturdays anymore. I'll be back on Monday morning, 5 a.m. And we'll pick up, wherever I leave off over the weekend. Monday, 5 a.m. next stream, 5 a.m. Mountain Time. If you look on my page, you'll see the schedule. See you guys. Bye.